Hello. Let's talk about the bugs. Specifically, some bugs are harder than other ones, right? Have you ever been there? You've been debugging something because you were called for firefighting, but because you have too many spinning tables, you feel that you've checked the same things for the third time, and you don't know what is happening. Or have you been there? Your team has been debugging for a few days. They step on each other's toes because it's very hard to manage this work, and nothing is fixed, and then your manager comes asking for a progress, and you don't know what to tell them because you don't understand if there is any progress in debugging. Or have you been there? You've reassigned a bug that arrived to some other team just to see that it's circled back after 3 or 4 days, going through 4 different teams with some nasty comments about the original reassignment, and you don't know what to do with this. Or rather, how many times you have been there, because that's the conference for StaffPlus engineers, right? So it's our shared experience. I have been there many times because I've been a software engineer for more than 12 years. I have seen those issues, and to be honest, when I see them, sometimes I reconsider my career choices. I think that maybe it's not the best place to be, and I even think that working remotely is perfect for me as long as it means working from a remote part of Polish mountains as a shepherd, not as a software developer from my home office. Still, I'm still a software engineer because I found hope, and I'm here to share it with you. I found a very effective way of debugging. I use it in my daily work at Chattermill when I work, and I want to share it with you. At Chattermill, we do some cool stuff because we fetch data about customer experience. We put it through dozens of ML models. I'm a backend engineer and I need to orchestrate this. So that's pretty complex, and there is some debugging involved, and I'm able to be very effective. And also, I noticed that the same approach is used by my colleagues independently from me. So I hope that it will be also useful for you and for your teams. I am here to tell you that you should debug like a scientist. You may ask me, Maciek, are you sure that we should debug like scientists? What do they know about bugs? They are folks of weird experiments, theories, and papers nobody reads, right? I would say that a bug is a surprising behavior of a system, a surprising behavior of a reality. And that's exactly what happens to physics in the end of 19th century. Physicists in the end of 19th century knew a lot about the nature of light. They knew the speed of light. They knew that light is both a particle and a wave. Still, they believed that the light needs a medium to be transferred. So they coined a hypothesis that there is the thing called luminiferous ether, and Earth moves through this ether. And they wanted to measure the speed of Earth in ether. They prepared a smart experiment. They sent 2 rays of light in orthogonal directions. They measured the difference, that there should be a difference, and there was none. The speed of light was the same. That bugged them, really. So there was a bug, so they patched it. They proposed some ad hoc hypothesis, but they didn't work until a young clerk from a Bern patent office came, and instead of yelling at the reality, he decided to describe it. He started with the basic observations that everybody knew, that the speed of light is the same on all frames of references, and the laws of physics should be the same in all systems. And he proposed some predictions based on those assumptions. And, you know, at the beginning, it was just a weird hypothesis, a weird theory. But year after year, it was confirmed by the experiments, and the other theories were rejected. And now that's pretty a solid theory. It's called special relativity, and we teach it to the kids in high schools. So yeah, it's probably true. Still, the gist of it is not the results, it's the method. They started with a weird behavior of the reality. So Einstein guessed what would be the explanation. He predicted the results of it, and then the other physicists were able to verify this theory and reject the other ones. And that's what I want to share here. Still, you may ask, it's quite removed from our daily work, right? The speed of light, Einstein, we are not Einsteins, right? So let me tell you three debugging stories. The first one, we had failures in our integration test. Back then I was working for a sizable company with hundreds of developers working on the same system. So when there was an issue with the integration test, this issue was blocking all the teams. And it happened that this error was raised from a library that my team added because we needed this library badly. It was an embarrassing issue because we were calling a method on null and a non-existing method. And in front of our virtual doors, we had a virtual mob. I was working remotely with virtual pitchforks, and the mob was yelling, "Remove the library, remove the library, remove the library. You're blocking us." And we needed this library badly, so instead of yelling, we decided to describe the reality and understand it and widen some context. So we started reading the source, and we found the place that was raising the error. That was pretty straightforward. The weird part was that we checked that with our config and with the source of the library, we can't reach this place because we returned earlier. We were looking around, and we noticed that somebody added a hook that was changing this configuration variable. So yeah, so it was still okay because they were changing it back. So why would it happen? And I thought, yeah, we reached a place in the code that we can't reach. It looks like a race condition. That's weird. I haven't seen it for a while. So I wrote on Slack, yeah, it might be a race condition, you know, I need to check this hypothesis. This is a wild guess, but I need to check it. And even though it was a wild guess, the stakes were quite high because I was promised a PhD in bugology. I'm still waiting for the certificate. So yeah, it was just it wasn't a guess, right? We are engineers. We are serious people. It wasn't a guess. I proposed a hypothesis. And I planned an experiment to prove that I'm right or to prove that I'm wrong. The experiment was simple. Instead of running in threads, I decided to simulate them just to make it more predictable. So in the same script, I interleaved two pieces of logic. The first is a business logic that was raising the error, and the second was the part that was changing the configuration variable. And I ran it, and bam, I failed successfully. I reproduced the error, and it confirmed my guess that it is indeed a race condition. And the problem was that this hook that was added later wasn't thread safe. So we got to the understanding. The problem was solved when we understood this. We were able to patch it quickly by removing that hook. And also, we were able to plan a long-term fix, and we were able to ask the other team to fix it because we had very good arguments for this. So what happened here really looks like scientific method. It's not that we are scientists, but the approach worked really well. When the reality started behaving in a surprising way, we started observing everything and widening our context. We connected the dots, guessing the hypothesis, and then we proposed a simple experiment to verify this hypothesis. And if it came up to be true, we came to the understanding and we were able to fix the issue. So what I learned here is that first is not to be the pitchfork guy yelling and jumping to the conclusion or to the solution, and second, to follow the guessing pattern, the scientific guessing pattern with hypotheses that could be rejected or confirmed, to connect the dots that seem to be pretty random. But still, it was a simple case. I reproduced it locally. What about the bugs that cannot be reproduced locally? It was another case of a bug in an integration tests. This time, it was rather in the infra of the test suite. When we started debugging this, we were in the dark, because what we had in our heads is that, yeah, the setup of the integration tests fails. This black box of the integration tests infrastructure just fails us. But yeah, we were still blocking hundreds of engineers, so we had to roll up our sleeve at work. The first thing that I noticed is that one of the containers weren't started properly. We weren't able to reach this container. So yeah, the infra failure, it's not for us, the developers, but let's try. So I was checking the code and I noticed that we sent a post request to this container. So I thought maybe this post is too big and that's why we have an error. I was totally wrong. I couldn't think like this. Still, I tried. Let's switch it to something simpler. Let's send them there ahead a very simple request, very small request, and let's see what happens. Oh, that's a different error. That's a read timeout. Let's write it down. And I didn't remember then what's the difference between different kind of timeouts. So I started checking online, of course, and I learned that if it's a read timeout, it means that the process there works, the port is bound, but the process just doesn't respond. So I thought, yeah, that's a step ahead. Why couldn't it respond? I started checking the bugs on Docker Compose because we were using Docker Compose to orchestrate our containers. And I noticed that if you log heavily and in certain conditions, Docker Compose could cause containers to freeze because there is a bug. And we indeed logged a lot from our health check endpoint. So I thought, yeah, maybe that's it. Maybe because of the bug in Docker Compose, we can't connect to this container. But I wasn't able to, of course, to upgrade Docker Compose to fix this bug in our CI infrastructure because it was too complex and too risky. I wasn't able to reproduce it locally, so I did the simplest thing possible. I stopped logging. And I checked it, and I hold my breath, and it worked. It solved the problem. So, of course, it was a simple patch, but it unblocked my PS, and I had very good reason to go to our infra team and to say, you know, guys, if you could in this or the next quarter upgrade Docker Compose, that would be really nice. And they understood me well because I had hard facts to support it. What I learned here is that when I don't understand something, I take a note and I write a question to myself. And I note everything that's remotely related to the debugging case, everything that looks weird, everything that looks off. I have everything in one place. And whenever I'm interrupted, and it happens very often, I can quickly get back to the place when I left off. And also, what I learned is to balance passive learning and active learning. When I enter the lab, just as I described, I write down everything just as a scientist in a lab. And I try many things, but then I get back to the library to learn how the things works and to build a mental model, just as in the science, you balance the theory with the experimentation. But still, those cases were a bit simple because I was a solo developer or a small team solo debugger, or I was debugging in a small team. What if we had a bigger case? Let me tell about the bug that wasn't just weird, It was preposterous, and it was embarrassing. Why? Because our production system was failing every 30 minutes, raising 502s. Everybody saw this, and the business was asking us, "Hey guys, what happens?" And the only answer from our side was, "We are checking." And it took us a few days of embarrassment of fixing this, and we didn't really know. That's why this bug was so bad. The symptom that we notice is that every 30 minutes, we notice a build-up in the request queue in our app server called passenger, and then it's resolved and everything is back to normal. And I joined a rather sizable task force that aimed to fix it, and we had a lot of hypotheses why it could happen. Maybe we have a cron job running every 30 minutes. Maybe there is a memory leak building, and it's building up because we have some memory buildups. Maybe we have denial of service, where maybe there is a very long request blocking everything. Maybe it's ourselves that do this DDoS. We noticed that there were regular restarts that coincided with the problem. And that was the moment where I realized that it's not only me who used the hypothesis-driven debugging, because people around me were proposing hypotheses and teaming up to verify them. So we were able to work in parallel, and we were publishing partial results. So we were flourishing, working together. And somebody noticed that there was only one node failing at a time. We had several servers, of course. So we knew it was a local buildup, maybe in the Debug proxy misconfiguration, maybe in web proxy, maybe we build up state on file system. But I was pretty sure it was a memory leak, and I wanted to prove my hypothesis true. So one night, I was so anxious to fix it that I started taking notes to correlate data from various sources. By the way, never debug at night. It was a bad idea, but yeah, I had to. So I noticed that at 10:12 it starts, then and after 4 minutes, the queue is saturated, and after 2 more minutes, it drops, and after half an hour, the problem arises again. And I added some more notes. I noticed that the first client timeout happened before. That was interesting, and the memory peak happens after the build-up. So I had to rule out the memory leak. I noticed that there is a peak of number of processes in our app server, but then the processes are killed. That's normal, but no new processes are spawned as they should be spawned. So I didn't know it. It was late at night, so I took a note on Slack and I sent it. I asked some questions. I ruled out my hypothesis about the memory leak, and I went to bed. And the next day, I had an answer from Argentina, because we were working in various time zones. And the guy from Argentina explained how the app server works, that if we have an error on startup, and we had an error on startup that we missed, the processes are not spawned. And that might be the reason that we have this problem, because the processes are killed until we get to the build-up. And yeah, why we have this error? We had the timeout error on startup. Somebody checked that whether we use a booting cache to speed up the booting process, but the cache was a little bit too big, and reading it took us more than 30 seconds. So actually it slowed down the startup process, and we did a simple experiment. We cleared this cache, and it worked. It started working. What we learned here, of course, that the hardest problem in the computer science is cache invalidation. But also, we noticed that it's a very effective way of scaling the debugging process. We were able to follow parallel. We work in parallel because we were testing in parallel multiple hypotheses. We were able to do this because instead of stepping on each other toes, we were standing on each other's shoulders because we were sharing the partial results. We were able to work round the clock because of this, not because we were tied to our chairs and keyboards because, yeah, production outage, but because our friends from the other side of the pond were able to pick up when we in Europe left off. And it was also a good metric of progress. We knew what hypothesis we rejected. We knew what weird hypothesis we still have. And because of this, we were able to tell about the progress to non-technical people. And also, it's a great tool to coach your junior team members. Instead of being a hero, you can let them to be a hero of their debugging by asking the right questions. So what's the weird situation that you are in? What's the weird thing that you notice around you? Okay, let's try to connect the dots. What's your working hypothesis about this? What's your other working hypothesis? How would you verify this hypothesis? Okay, this experiment will take you 2 days, right? That's right. So it's too long. Try to verify this hypothesis in just 2 hours. Oh, okay. You rejected it. So what's the next step? You can let them fix the problem, and that's how you can scale yourself and your debugging skills to the entire team, and you make them happy. So this was the great moment when I realized we can scale debugging by working like a scientist, because the scientific community in perfect world, they publish theories, somebody else publishes an experiment confirming the theory, somebody else redo the experiment, and in this asynchronous and decentralized manner, the science is pushed forward. And that's how we can push forward in a decentralized and asynchronous manner our debugging process, our team debugging process. That's also a great way to coach people and to talk to outside stakeholders. So we started with this hard moment, right? We started with desperation and looking for posts for junior shepherds, right? But finally, I told you that we don't have to change our jobs, and I hope that I convinced you. And the way out of this desperation is in science. That is not in scientific results, but rather in the scientific method, in the habits used by scientists, because they let you lay the foundation by going after the understanding, not the simple solutions, by testing hypotheses, and also by the good habits of taking notes, asking open questions, noticing weird things, and balancing the passive and active learning. And when you use this approach, you can scale the debugging to the entire team, and you can inform the entire organization about your progress because you can understand this progress. But there is one more thing, one last practice that's crucial to make it really working. When you debug, you learn something the hard way. And when we have PhD students, we ask them to teach their younger peers, the graduate students, the basics of their field. And it's not only because the university is understaffed. We do this also because that's the great way to make sure that the PhD students really understand the basics. And I believe that's something that we should also do in our teams. When we finish the debugging, when we acquire this understanding, we need to teach it to the others. Write a note on Slack, do the postmortem, come to a conference, or just share the story over a beer or a juice to your friend. And I believe that we should encourage, especially our senior developers, but also the younger ones, that they must share their knowledge, not only to spread it within the organization, but to make sure that this knowledge sticks into their heads, and that the learning that we acquired in a painful way is not lost. And that's the top of the scientific debugging pyramid. I hope that I convinced you that you don't need to be a shepherd, but instead shepherd your team to be effective debuggers. Thank you.